And please,
Okay.
your lecture.
Thank you very much. Yeah, thanks for everybody who came online and in person. So I will continue this cycle of lectures today. And last time we talked about positive definiteness extensively, and today we'll see some applications of this property. In particular, mostly we will talk about the so-called linear programming method, which is very helpful for both discrete and continuous energies. And in particular, it's also helpful in finding optimal spherical codes, or packings on the sphere, at least in some situations. Okay, so let me just briefly remind some things from yesterday. So our notation is the following. We'll deal mostly with the continuous kernels on some compact domain omega, continuous and symmetric kernels, and we will consider continuous energy functionals or energy integrals, which look like this, where mu is some Borel probability measure on omega. And similarly, we will consider discrete energies of this type, and I will usually normalize them by 1 over n squared, if we had a set of endpoints, just so that this definition becomes compatible with the definition of the energy integral in this sense. So it's the energy integral applied to this empirical measure. Okay, and we have talked about positive definiteness. I will not necessarily remind, well, I can remind the definition really quickly. Let me find it in the previous slides. So positive definiteness means, in terms of the energy integral, that for any signed measure, the energy integral is non-negative. Okay. Or for any choice of points, you have this matrix K applied to all possible pairs of points. This matrix is positive semi-definite. Okay. All right, and what we have talked about last time, the general situation where there exists a K invariant measure, and that's a measure for which the potential, that is, if you integrate the kernel with respect to that measure just once, is constant on the whole domain. So these measures are called K invariant, and we talked that for one of the most important examples for us for today will be the sigma the normalized uniform surface measure on the sphere. Okay, it's if your kernel is rotationally invariant, if it depends just on the relative position of the 2 points, then this measure is invariant. And another example which is relevant to today's talk is, again, if your domain is the sphere and your discrete set of points is a design of strength n, and we'll talk about designs in more detail a little later, and this rotational invariant kernel is a polynomial of degree n, then also this is going to be an invariant measure, and the potential is going to be constant on the whole sphere. So these two examples are going to be important for us. Okay, and in particular, the first one. So for now, let's keep in mind the first example. Okay, and let me just remind you all these properties that we've talked about yesterday. So if you have a positive definite function, or okay, if it's positive definite modulo a constant, of course, for energy minimization, a constant doesn't play any role. This is equivalent to a bunch of different things. In particular, this is equivalent to conditional positive definiteness when there exists. So all this is under the assumption that there exists an invariant measure with full support. Okay, and in terms of energy minimization, this is equivalent to several things. This is equivalent to the fact that this invariant measure is a global minimizer over probability measure, that it's a global minimizer over all signed measures. So this P tilde is the set of signed measures of mass 1. Okay. Also, it's equivalent to the fact that it's a local minimizer, for example, in the directional sense, okay, or in some other senses. Okay, so I'll get to some other parts also, but already right away, this tells you something about the sphere. if you have a rotationally invariant kernel on the sphere, which is positive definite, you know right away that the uniform measure minimizes the energy integral over the sphere, among all probability measures, and even among all measures, among all signed measures of mass one, which is quite interesting because it's generally not absolutely obvious that if sigma is a minimizer among all measures, then it will also be a minimizer among, if it's a minimizer among all probability measures, positive measures of mass one, then it also will minimize over all signed measures. So this turns out that on the sphere it is automatic. You can this cannot fail. Okay. But of course, it would be nice to understand what functions are positive definite on the sphere. Okay, and in particular, this last part, which we talked about yesterday, would be important. So we know that if a function is positive definite, if you write down the Hilbert-Schmidt operator, the integration operator, which is just integration with this kernel. And this is going to be a compact operator on L2 of mu. And well, you can write, and it's if the function is positive definite, the kernel is positive definite, then this operator is going to be positive, which means that its eigenvalues are going to be non-negative, and you are going to have this expansion, okay, where these are the eigenvalues, or these are the eigenfunctions, and the eigenvalues have to be non-negative. Well, maybe among at least starting from j equal to 2, maybe except for the first one, because here we're only assuming that it's positive definite modulo constant. So the initial eigenvalue corresponding to the constant function could be negative. Okay. And also we know that this series converges uniformly and absolutely from Mercer's theorem, which is very nice. Okay, so this allows us to understand what functions are positive definite on this sphere. Okay, so the eigenfunctions of the Hilbert-Schmidt operator in this case are exactly the spherical harmonics. So spherical harmonics are homogeneous polynomials of degree n. Harmonic homogeneous polynomials of degree n. They're also eigenfunctions of the Laplace-Beltrami operator on the sphere. There are many different ways to approach this theory. I will not go too much in detail. There is a sequence of associated polynomials on -1, 1. So these are polynomials which are orthogonal with respect to this weight. Again, this weight essentially, yeah.
It's not visible. What's on the top right? Kxy is equal.
Okay. Okay, it just says f of x dot y.
Sorry.
Yeah. Yeah. So your kernel is rotational invariant. Right? Okay. All right. Okay. This weight, with respect to which you're taking orthogonality, is the weight that arises when you integrate over the sphere, where you have zonal functions, integrate them over the sphere in cylindrical coordinates. Right? Actually, this weight disappears when you're on S2 in dimension 3. That corresponds to the famous result that goes back to Archimedes, that if you take a sphere and a circumscribed cylinder and you take horizontal sections, then the areas are the same. Okay? And there is a legend that Archimedes liked it so much that this was carved on his tombstone, but that did not survive to our days, so we don't know. Unlike Boltzmann's tombstone that Thomas mentioned in his talk, this we have no way of confirming. Okay. All right. So there are various ways to define these polynomials. There are various normalizations, various notations. I'm using maybe. By now, this is a slightly less standard notation. This I'm following the notation of Delsarte, Goethals, and Seidel. So they were using Q for Gegenbauer polynomials, and the normalization that I'm using will become clear in a moment. Okay, but basically, since these are orthogonal polynomials, any function, any L2 function or any continuous function can be expanded into these polynomials, at least in the L2 sense. We'll write it like this. And there are several interesting facts about spherical harmonics that are related to this expansion. So first of all, the fact that they are eigenfunctions of the Hilbert-Schmidt operator just follows from the so-called Funkeke formula, which tells you that if you integrate f of x, y with any spherical harmonic, let me call it h sub n, this is a spherical harmonic of degree n. That is just going to be the nth Gegenbauer coefficient of f times this spherical harmonic at x. So spherical harmonics are eigenfunctions, so this is known as the Funkeke formula. And another important fact about spherical harmonics and their relation to the Gegenbauer polynomials is the so-called addition formula. So the addition formula tells you that if you take any orthonormal basis of the space of spherical harmonics of degree n, so I'll denote it by h and d. D is the dimension and n is the degree of spherical harmonics. So if you take any orthonormal basis and you construct this sum, okay, this sum depends only on the relative position on the points x and y, and the dependence is precisely through the Gegenbauer polynomial. Okay, right. Well, if we now take x equal to y in this formula, we will get on the left-hand side, you just get the sum of squares of the elements of the orthonormal basis. And on the right-hand side, you get Qn of 1. Right? So you find that the sum of squares does not depend on x. And now if you integrate this, since this were an orthonormal basis, you will just pick up the dimension, right? Because each term will give you one once you integrate. So, and this explains our normalization. Our normalization is such that at the point t equal to 1, the Gegenbauer polynomial gives you exactly the dimension of the space of spherical harmonics, and it's known that how to compute this dimension, that's precisely the dimension of the space of spherical harmonics. Okay. So from here, it becomes quite clear what positive definite functions on the sphere are, right? So in particular, you know that, well, if you go back, sorry, if you go back to this decomposition, you want all the coefficients here to be, all the eigenvalues to be non-negative, okay? Well, and the eigenvalues are precisely the Gegenbauer coefficients of the function f. Okay. Because here, this follows from the Funkeke formula. So this may be not the most standard way to describe this theory, but this, this shows how this follows from a very general approach, okay? So now this tells you that the function f is the kernel of this type is positive definite on this sphere if and only if all the coefficients, all the Gegenbauer coefficients are non-negative. Right. So this results, and of course it was proved somewhat differently, but this goes back to Schoenberg. It's proved back in the 40s. Okay. So for every function, now we know that for every function of this type, the sigma minimizes the energy integral. So the let me write it. Write it slightly different. So this is minimized by sigma, by the uniform measure. Okay, and one other fact that we will need is that actually, well, what's IF of sigma? Okay. Well, it's actually easy to check that that's exactly equal to the zeros Gegenbauer coefficient. Okay. So the zeros Gegenbauer coefficient just gives you the average value of F on the sphere. It's a common trend, and it's in all natural orthogonal expansions, the zeros coefficient is the average value of the function. Okay, so here it's the average value of the function F on the sphere. Okay. Well, here we start with zero. So unlike this general theorem where I started from 1, here we start from 0. Yeah, I probably should have started from 0 in the general theorem also. So 0, the one that corresponds to the constant function. Okay. So here the index is the degree. Okay. All right. So right, and it's clear also that now it becomes clear that the Gegenbauer expansion is compatible with the spectral expansion, because you can, if you write the Gegenbauer expansion of F, and then you use the addition theorem, you just plug in this expression. Now this becomes exactly the spectral expansion of F, the spectral expansion of the kernel that we saw in the theorem. Okay, so all these things are very much compatible. Okay. Right. Also, well, just for future reference, let's look at this quantity. We will need this several times. If you take any set of points on the sphere and you compute this, so you compute the energy essentially with the kernel given by the Gegenbauer polynomial. Well, you can use the addition formula. Okay. You can take this sum inside, right? And then you would just get the following expression. The sum inside, the two sums inside will split into a product of identical sums, so you'll get a square. So this will be the sum over sorry, this is Zi and Zj, my apologies. Nk Zi squared. So this is non-negative. Okay. And also you can even see when it is going to be 0. It's going to be 0 when all the sums inside are 0. Okay. And well, that means that these sums give you the same thing as the integral, because orthogonality, the integrals of all these spherical harmonics are 0. So you will get zeros for spherical designs. That will be an important fact. Okay, so now with all of this preparation at hand, we can finally approach the linear programming bounds. And I first state the variation of the linear programming bound for spherical codes, okay, for separated sets, for packings on the sphere. Okay, so assume you have a function f with the following Gegenbauer expansion. Okay. So we have that all the coefficients are non-negative, and the initial coefficient, the zeros coefficient, is actually positive. Okay. Also, we have the property that the function, and sorry, this should be capital F. The function capital F is negative for tau below a certain value alpha. Okay, then assume you have a spherical code of size n with separation alpha. And here I measure separation not in the Euclidean distance, but in the inner product. So that means that the inner product between any two distinct points is less than or equal to alpha. Then the number of points in this spherical code is bounded above by f of 1 divided by the zeros Gegenbauer coefficient. right? So this gives an immediate upper bound on the size of the spherical code, if provided that you can find such a function. Okay, so the function has to be, these two conditions say that if your function is positive definite, right, according to Schoenberg's theorem. Okay, and you need an additional condition that the function is not positive for tau below alpha. Okay, well, the proof is very simple now with everything that we know. And again, the way I will state this proof will be a little bit non-standard. Of course, you could just write f in terms of Gegenbauer coefficients, rearrange all the terms, and this would be a more standard proof. But we can now just use more general theory to rewrite this proof slightly differently. Okay, so let's look at this object. Let's look at the discrete energy. Okay. On one hand, whenever I is not equal to j, the terms are negative or non-positive. Okay, that's why it's less than or equal than just the diagonal terms, okay, which just gives you f of 1 n times, and you divide by n squared, so you get 1 over n. Okay. On the other hand, so this is the discrete energy, which is equal to the energy integral on this empirical measure. Okay. So this is bounded below by the minimal energy. Okay. And we've discussed that for positive definite functions, our f is positive definite. The minimal energy, the energy is minimized by sigma. And we also discussed that that's actually equal to the zeroth Gegenbauer coefficient. So to obtain this bound. And technically, this variation of the proof shows to you that if for some other reasons you knew that some other measure minimizes the energy integral, so if you didn't assume that f is positive definite, but you have another some other function, you know the energy minimizer, you would have this bound. Unfortunately, in most examples that we know, most energy minimization examples come from linear programming, so that doesn't usually help you. But generally, this bound is true whenever you know the minimum of the energy over probability measures. Okay. One application of this is to Kisin numbers. In particular, the Kisin numbers, which I mentioned in the first lecture. So remember what it is. The Kisin numbers are essentially spherical codes of Euclidean separation 1 or angular separation 60 degrees, right? Or in terms of the inner product, separation is 1/2, right? So you want spherical codes with separation 1/2, okay? And well, I mentioned in the first lecture that this is solved for dimensions 8 and 24, so independently by Dlisco-Sloan and by Levenstein. Okay, and in the dimension 8, this is the E8, the roots of the E8 lattice. In dimension 24, it's the roots of Leach lattice. This can be done directly using the inequality that was described a couple of slides ago, the linear programming bound. You just need to find the right function, and it's quite easy to find that function knowing the properties of these sets. Well, basically in the E8 lattice, all the inner products will take these values. So you construct this polynomial, okay? And the hard part here, but it's a direct computation, is to show that it's positive definite. So one way there are several ways to show that it's positive definite. One of them is just do it directly, expand it in terms of Gegenbauer polynomials. Okay, so and obviously because of this t to the t minus 1/2 here, when t is less than 1/2, notice this is just power 1, not squared. This will be negative. So and then this gives you exactly the right bound for the Kisin number in dimension 8, if you run this computation. And for the Leach lattice in dimension 24, there is an extra value of the inner product plus minus 1/4, and it works the same way. So magically it all works out. The function, this most natural polynomial, turns out to be positive definite, and it turns out to give you the exact bound. All right. Let us look at some other applications of the linear programming method. Again, some classical applications. So let's talk about spherical designs and the sizes of spherical designs. So spherical designs are discrete sets such that averages over them, averages of polynomials of degree up to some given t, are equal to the averages over the whole sphere. The integral over the whole sphere. So discrete average is equal to the continuous average. Okay, and equivalently, this property can be stated as follows, because all polynomials can be represented through spherical harmonics. So you can just restrict to the Gegenbauer polynomial. So this more energy-related statement is equivalent to the definition of spherical designs, that the discrete energy over this set Z is equal to the continuous energy with respect to sigma, and this is actually equal to 0 for k greater than 1, because spherical harmonics of different orders are orthogonal to each other. Okay, so this is an interesting property. Now, if we look here, so this, remember we had the inequality that this sum on the left for an arbitrary point set is greater than or equal to 0. So this says that spherical designs minimize this continuous energy. They give you exactly 0. They are minimizers. Of course, sigma also minimizes this energy. So here you see that you have this continuous minimizers, absolutely continuous measures and minimizers, and you have discrete minimizers. All right. So there is an analog of the linear programming bound for spherical designs, which gives you a lower bound of the size of spherical designs, and this is due to Delsart, Goethals, and Seidel. And it tells you the following: assume you have a function with the following properties, that it's non-negative and it's strictly positive at 1, okay? And its coefficients, its Gegenbauer coefficients are 0 above t, above some specific value t. So then if you have any spherical t design, then its cardinality has to be at least this same ratio. Okay. The proof is, again, quite simple. You write down the discrete energy. Okay. And you can just, you rewrite it like this. You expand F. And you put this sum inside. Okay. And this sum is non-negative, right? And well, if the coefficients are, so you can drop all the coefficients above k. So first of all, you can drop all the coefficients below k, because if we assume that this is spherical design, so all the coefficients below t give you 0. Okay, so you're just left with the sum over n squared, the sum over k starting from t plus 1 to infinity, fk. Okay, and let me write, okay, the only one, sorry, I made a little mistake. The only coefficient that didn't vanish is F0. Okay. F0 didn't vanish. That's still here. Okay. All right. And yeah, and all of this is negative because these coefficients here are non-positive. Okay. Well, on the other hand, this is just bounded below. Since the function is positive, you can leave just the diagonal terms here, and you will have 1 over n times f of 1. Okay. And you get the bound again, right? Okay, so this bound now, this theorem lets you find lower bounds for cardinality of spherical designs. And well, again, the main problem is to find the function that fits the bill. Okay. And well, so this is a theorem of Delsart, Goethals, and Seidel, that you have these bounds for spherical designs. I will show you one of the proofs in the case when t is even. Okay. Notice before we do it that in both cases you have that the cardinality is at least of the order t to the power d minus 1, the strength to the power dimension of the sphere. Okay. It was so you need at least this many points, at least asymptotically. It was an open question for a while. It was conjecture of Korevar and Meyers whether this is actually enough, and several years ago this was solved by Bondarenko, Radchenko, and Vyazovska. So they proved that this many points is actually enough. There exist spherical designs of roughly this cardinality. Okay, but now I want to explain to you how to prove this bound, and this bound can be proved in the following way. So the polynomial that we want to construct is the following: we take all the Gegenbauer polynomials of degree up to m, okay, and we take their sum and square it. So that's going to be a polynomial of degree 2m. And you can easily compute the value of this polynomial at 1, because remember we had a specific expression for each Gegenbauer polynomial at 1 that was just the dimension of the space of spherical harmonics. You get telescoping sums, and then you just get these two terms. Okay, so it's basically this is the dimension of all spherical harmonics of degree up to m, so all polynomials of degree up to m. Okay, and then, well, I will not do this, I will save some time, but basically using the addition formula, you can also compute the zeros coefficient. Okay. So you can use the fact that it's just the integral of the function over the sphere, which we've discussed. Okay, and then you square this out and use the addition formula. I will not finish this computation, you can do this, but that, yeah.
Just one small remark to this computation. It's not written in the paper, but the polynomial they take is actually chosen to be optimal with respect to that. So it's a polynomial with the largest value at 1, even the integral.
Even the integral, yeah. Mm-hmm.
And positive, of course, because it's a square.
Right, yeah. Mm-hmm.
So you can't do better than that with a polynomial.
Mm-hmm. Yeah.
And a second remark, there's a follow-up paper of Udin that's not that well known as the Delsart-Seidel paper, which improves that bound by taking a more complicated function, so not a polynomial.
Ah, okay, interesting. But this bound is exact sometimes, so it improves it in the cases when this is not exact, when the Delsart-Seidel is not exact.
It's improving the bound of the Delsart-Seidel by a factor actually. So it's the same order of magnitude, of course, n power or t power m power d, t minus 1, but the constant in front is larger.
So, okay, yeah, we can discuss later, but the point is that this inequality is actually there are spherical designs where this is achieved.
But only for small numbers of m.
Yeah, only for yeah, I'll get to it in a moment. Yeah. Okay. So what you get here, you'll get the exact same value. So you'll get UKF1. So basically, you can probably see how to finish this computation. And for sk runs from 0 to m. Okay, and well, then you'll have your bound will be this quantity squared divided by this, which is the same thing. So you just get this quantity and you get this bound to the right-hand side. All right, so this is the proof of the lower bound in the case of even strengths of the design. Okay, and designs for which these bounds are achieved are called tight designs, and it's known that they exist. There are not that many of them, so these are tight designs. They only exist. Well, okay, on S1, on the circle, they exist for all n. You just take regular end-ons, but things are not as good in higher dimensions. Basically, for d greater than or equal to 3, there is only a few of them, and they can exist for strengths 4, 5, 7, and 11. Leech lattice gives 11. Okay. Right. Also, one can show that tight designs are also optimal in terms of the number of distances that they generate. So tight designs, if you have an odd design of odd strengths, it has m different distances between distinct points, including -1. And when I say distance here, I really mean the inner product. Okay. And so it includes -1. -1 corresponds to opposite points. Actually, even in this case, in tight design of odd strengths has to be symmetric. Okay, and the tight design of even strengths 2m has m distances. So actually, you have the opposite bounds. If you want an m distance set on the sphere, its cardinality cannot be greater than the bounds given in the Delsart-Gerolsteidl theorem. Okay, so in this way, these two notions match together precisely at these values. Okay. Yeah, so here is a table of the known tight designs. The only part of this table that's not really, this is the 600 cell is not a tight design, but it's because it skips 1 power actually, but it has a lot of properties which are very similar. So yeah, so as you can see, there is only about 10 of them known. Okay, and I will return to tight designs in a moment, but right now I want to show to you how to relate energy estimates to linear programming and to positive definite functions. We already know that if your kernel is positive definite, then you know exactly what the energy minimizer among measures is. That's sigma. That's the uniform measure. Okay. Well, assume we want to deal with discrete energies, and in the case when f is not positive definite. Then what you can try to do is you can try to find a function that is a lower bound for f, which is positive definite, okay, for which you know what the energy minimizer is, and that will give you a bound on the energy of f. It would give you a bound on the energy integral, but also very often this approach is used for functions which are singular at 1. So remember, 1 here corresponds to the fact when the 2 points collide, right? So when they coincide, inner product 1. So in this case, you don't want to take the diagonal terms here, so you can use it for singular functions also. And again, the proof is pretty easy. You have that. Let me still normalize the left-hand side, n squared. You just use the fact that f majorizes h. And now I'll drop the condition that I is not equal to j. But then I'll have to subtract back, and sorry, this was supposed to be capital H of 1 times n times n diagonal terms, right? And again, if this function here is positive definite, the discrete energy is bounded below by the minimal energy over all measures. Okay, so that's bounded below and by 1 over n squared times the minimal energy, which is just the energy of h at sigma, which is equal to the zeros coefficient of h minus h of 1 times n. And we have the bound multiplied by n squared. Right. I'm sorry. Yeah, this is 1 over n. Here I don't need it. Sorry about that. No. That is correct now, I think. All right. And this approach can be used very efficiently in some situations. In particular, I want to take a few minutes to talk about universal optimalities. Okay, so this is a result in the notion introduced by Kohn and Kumar. And the statement is the following. The statement is that any 2m minus 1 design, which has only m distances between distinct points, they call it sharp configurations. That's with these two properties. This okay, is universally optimal in the following sense: the discrete energy of this type is for n-point sets among so these configurations minimize the n-point energy for all functions which are absolutely monotone, and absolutely monotone means that all the derivatives are non-negative. Right. So let me try to explain the idea of the proof. The idea is exactly based on this theorem. By the way, this theorem, I think, goes back to Udin. Again, the problem is that you need to find this function. Okay. Well, how do you find this function? Draw a graph and try to explain the idea. Okay, well, here's your function f. And here are the distances of the m distances of your set. So this method works very well when you have a candidate. It doesn't help you find the minimizer, but if you have a candidate for a minimizer, this works well. Now let's just try to find the function h, which will be below f, but which will coincide with f at those points. How do you do that? Well, you interpolate, okay? You do so-called Hermite interpolation, okay? You need to match not just the value at this point, but also the derivative. So basically at each point here, you're using 2 data points. That explains why you need few distances. Okay? So the idea here, without checking all the numerology, is that you want a design of high strengths with few distances, because the number of distances will determine how many data points you're using in the interpolation. Okay? And that will determine the degree of the polynomial that you get by interpolation. Okay? And then you need the fact that this is a design. Okay, well, if we go back here, if H is a polynomial, so far here in this theorem itself, we haven't assumed that H is a polynomial. But if H is a polynomial, when is this exact? Well, this is exact precisely when Z is a design, right? As we've discussed a few minutes ago. Okay. So you want this to be a design of sufficiently high strength so that H gives you the same value on the design as on sigma, so that this inequality becomes equality. All right, so this is the idea of the proof. Let me just, okay, so I will just say a couple more words and I'll finish here. So one interesting thing is that you can already use this universal optimality to go back to spherical packings on the sphere, optimal spherical codes. So this would show that such configurations, the sharp configurations, are optimal codes, okay, that they have the optimal separation on the sphere. Okay, and this is done in the following way. If you remember some things from lecture 1, if we look at the Rees energy, okay, that is the energy with this kernel. This kernel is singular, but that's fine because 2 slides ago, we specifically discussed that this applies to singular kernels as well, as long as the lower bound that you find is a nice continuous function. And in our case, it's a polynomial. Okay, so if you rewrite this kernel in terms of the inner product tau is x dot y, right? Then you get this. You get this expression. Now it's very easy to check that this is absolutely monotone. Well, every time you differentiate, you pick up a negative power and then a negative sign from here. So all the derivatives are going to be positive. So for all Rees energies with any positive value of S, sharp configurations are minimizers. Okay. Well, remember, if you take S to infinity, the Rees energy becomes the optimal separation. Okay. So this tells you that that sharp configurations are optimal codes from the point of view of separation. And this gives you a way to prove that any of the sharp configurations, in particular, by the way, sharp configurations are, well, tight designs are sharp configurations, but there are more. Well, in particular, anything from this list, all the tight designs are optimal codes. In particular, this proves the optimality of the icosahedron and of the Leach lattice of E8. So you can deduce it from here. Okay, this is one of the ways. All right, and I'll stop here and I'll continue talking a little bit more about the linear programming method tomorrow.